where the meaning behind all of this comes. And we got down to the very end, and we got an equation that could be used to find the slope at any moment on that function. So at any x value, we could just plug that x value into here, and we would know the slope at that x value. So the notation for this, I did not get to this yesterday. If the function notation is f of x, the derivative of the function notation is f prime of x, is how you would read that. So f prime of x in this case is 2x. And so what we were asked to do was to find the slope of the tangent line at negative 1/8. That's the same as if we were asked to find the slope of the function at negative 1. So the notation for that would be f prime of negative 1 equals 2 times negative 1, which is negative 2. In human words, this says the slope of our function at an x-coordinate of negative 1 is negative 2. Okay? So on your homework, you will be asked to find the slope of the tangent line at a specific location on a function, or you might be phrased as you're just asked for the slope of the function at a specific location. But you're also going to be asked to write the equation of the tangent line. And in order to write the equation of any line, you need two things. What are they? Doesn't ask us here, but we're going to do it. What do you need? What two pieces of information do you need in order to write the equation of any line? You don't have to have the y-intercept unless you're doing it in this format. But if you're using this is called slope-intercept format. This is called what format? Point slope. And that's not a very creative name, because those are the two things that you have to know, a point and a slope. So right now, if we wanted to write the equation of the tangent line at negative 1/8, so that would be like, visually, that would be like us writing the equation of this line at negative 1/8. We have the point, so the point is negative 1/8, and we have the slope at negative 1, because we found it to be negative 2. And we would essentially just write the equation now. Y minus 8 equals negative 2. X minus negative 1 will turn into x plus 1. So we plug in x1, y1, and m, and there's our equation in point slope form. So you can write an equation, Olivia, without the y-intercept. If they do ask for it in this format, I would still write it here first, and then I would just distribute my negative 2 and add 8 to both sides. So y equals negative 2x plus 6. So just because it's fun and it helps us thoroughly see what's going on here, the function that we've been looking at is this x squared plus 7. And the equation of the tangent line at the point negative 1/8, we just wrote to be negative 2x plus 6. And when you grab... silly background. Is this happening? Is it this class that this always seems to happen in? I always grab that one. All right, we're starting over. X squared plus 7 and negative 2x plus 6. So there's your parabola, and here comes your tangent. Not the best window, because my graph has been shifted up so much, so maybe I change my window from 0 to... Nope, I like negative 10 to 10. I want 0 to 20 on my y-axis. And then we'll get a little bit of a better look at that tangent line. Right? You can kind of see that it's only hitting it once. If you're in doubt, you can zoom in, and you can bring your cursor right over to approximately negative 1/8. And here's your parabola, and here's your tangent line. And it really kind of shows you that one point of intersection. Not only that, we can do second trace, and we can intersect to show first curve, second curve, guess that that point of intersection is negative 1/8. One thing I will talk about is look at that point of intersection technically. It says negative 1.000000001 and 8.000000012. I've never really been able to find a good explanation for why it's not giving us the exact point, other than the lack of quality of the computer pixels, to be honest. That's always the explanation I've understood or heard. So if you get something like that where there's a lot of repeating zeros, you can just pretty much assume that that's negative 1/8 in this case. Okie doke? All right, so from the top, and with a little bit of a more difficult function. So let me give you first the visual. So we remember what it is we're doing here. Here's the function radical x. You should know that that's a parent function. And we're looking for the slope of the tangent line at 16,4. So let's just pretend that's the point 16,4. Do you expect your slope to be positive or negative there? You should expect it to be positive because it is increasing. If I were sketching a tangent line, it would look something like that. So it is a positive slope, not very positive though. These radical graphs kind of even and flatten out pretty quickly. They're never perfectly flat with a slope of 0, but they get pretty flat with a slope of like 1/100th. Is not out of the realm of possibility. So that's essentially what we're doing. We're looking for the slope of that tangent line, which will be the same as the slope of the curve at that point. So to find the derivative, or in other words, to find f prime of x, an equation for the slope of the derivative, you have to memorize this. It's the limit as h approaches 0. So again, it's really going to give us, it's the slope formula between 2 points that are h units apart, but we're kind of pinching those 2 points together, and that's where the h is approaching 0, because the closer those points get, the more that secant line turns into the tangent line. So it's the limit as h approaches 0 of what ends up being the difference quotient. So it was originally y2 minus y1, x2 minus x1, but then it's simplified down to the difference quotient. So it's the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x all over h. And so as we do this, as annoying as it's going to be, you need to, because otherwise you would lose points on an AP exam, you need to carry this limit as h approaches 0 down the entire time, while we're slowly cranking through this difference quotient. So what would f of x plus h look like? So I'm going to do an f of x plus h here, minus f of x all over h. That's my structure. Morgan, what would f of x plus h look like? Where's the plus h? Inside the radical or outside the radical? No. Inside. F of x plus h, and that's the mistake that a lot of people do make, is they put the plus h after everything. F of 7 would mean you plug in 7. F of b would mean you plug in b. So f of x plus h means you literally plug in x plus h. Does that make sense? Okay. So x plus h would still be under the radical. Minus f of x is just minus root x. You just copy that function over, all over h. So I put those brackets in there for organizational purposes. If these were polynomials, that would be more helpful. But to be truthful, the radicals kind of keep that x plus h grouped together anyway. And You don't really need those brackets. So if I were to try to find the limit as h approaches 0, my numerator would be root x minus root x, which would be 0, and my denominator would be 0 if I were directly evaluating. Well, there we have an indeterminate case, right? So what would be our manipulation technique here? Would it be factoring and canceling? No, nothing's factorable, right? Would it be clearing complex fractions? No, we don't have complex fractions. Would it be rationalizing? Absolutely. And in this case, we're rationalizing the numerator. So what would I multiply by to rationalize here? Nate. Nope. These radicals are a part of a binomial. Whenever we're rationalizing a binomial, we multiply by the conjugate of the binomial. So what is the conjugate of this binomial? Perfect. Radical x plus h, nice job, plus radical x. Radical x plus h plus radical x. Now, we're rationalizing the numerator, so that's the only one we're going to actually multiply out. Again, when we do this, as annoying as it's going to be, we're going to keep our limit as h approaches 0 there. Our first times our first gives us what? Sarah? X plus h. Our outers and our inners should cancel without thought, because that's what conjugates do. That's why they're beneficial. And our last times our last Connor would give us what? Minus x. Perfect. On our denominator, we're just going to leave that as h as a coefficient being multiplied by this conjugate binomial. And what we like on top is that the x minus the x will cancel, leaving just an h on the top and a factor of an h on the bottom, which is, now hopefully you see why we did not distribute that h. Because the h's cancel, h over h is 1. So this is the limit as h approaches 0 of 1 over root x plus h plus root x. Okay? So I've manipulated, I've changed the appearance. Now, reevaluate. If I plug in an h of 0, I now no longer need to write the limit as h approaches 0, because I'm actually doing direct evaluation right now. 1 over root x plus 0 plus root x, which is 1 over root x plus root x. And root x plus root x is what, John? How many root x's is this one? What coefficient is in front of that? 1 root x plus how many more? So 2 root x, okay? Root x plus root x is 2 root x. That's your derivative formula. It's not 0 over 0, right? So f prime of x is 1 over 2 root x. Good? So now let's actually answer their question. What is the slope at 16,4? So we need to find f prime of 16. The slope at 16 is 1 over 2 root 16, which is 1 over 2 times 4, which is 1 over 8. And then, let's write the equation of that tangent line, because these are the two parts that you're going to have to do on your homework. So to write the equation of the tangent line, we have our point, 16,4, and our slope, 1/8. We knew it was a pretty small slope, right? We said that. 1/8 is pretty small. Write your equation, y minus 4 equals 1/8 x minus 16. And if it wants it in slope-intercept form, which is y equals mx plus b, then you would go ahead and distribute and get y all by itself. But for now, we'll leave it like that. Okay? Couple things, we're done with this question, but there is a little bit more that's worth discussing just because we have the time today because I split these 2 days up. Where would this derivative be undefined? Where would the slope be undefined? What x values? Negatives, right? Because if we have negative x values, that would be imaginary type stuff, which doesn't really apply here. We would just stop there and say doesn't exist. Negatives and 0. When you look at the graph of the radical x function, can you see why you would get an undefined slope when x is in the negatives? Why? Because the graph doesn't even exist over there. This you might not see as well. Why is there an undefined slope at 0? Because the graph does exist there. And the rule is pretty simple. There is no slope at an endpoint. Okay? As soon as you get even microscopically beyond 0 to like positive 1 million, there's a slope there. But there's never a slope at an endpoint. Slope does not exist at an endpoint. So I'll take you back to like your interval notation. Do you remember back in the day if I said, on what interval is this graph increasing? You would say from 0 to infinity, right? In interval notation, first of all, infinities always have parentheses, but you were never allowed to use brackets on increasing, decreasing, or constant intervals. Do you remember that blanket rule? Like on positives, you could, and on negatives, you could, meaning above the x-axis and below the x-axis, you could use brackets. But when it was increasing, decreasing, or constant intervals, we never used brackets. Because at an endpoint, it's not actually doing either. Okay? It has to have been like a continuation in order to be increasing through 0. So it was easy to make a blanket rule back then, but this is really why. And our derivative stuff shows us that endpoints have no slope. Okay, doke? Okay. All right, find the slope of the tangent line to f of x equals 4x plus 2 at 1, 6. So let's just find the derivative, jump right into it. So f prime of x, your derivative, is the limit as h approaches 0 of the difference quotient. Which then becomes, what would Aiden, tell me what you write for f of x plus h. You don't need to simplify it out, just tell me what to initially write. Correct. There's f of x plus h with an x plus h plugged into the function, minus your f of x function is just 4x plus 2 all over h. Unlike the last problem, these brackets are definitely helpful for one, organizational purposes, but number two, if you don't have them on this minus f of x, then you're not technically distributing the negative, and you have to, okay? So when I continue my simplifying and continue writing down the limit as h approaches 0, I get 4x plus 4h plus 2 minus 4x minus 2, thank you, all over h. And what I love about this is 4x minus 4x cancels, 2 minus 2 cancels, and I'm just left with 4h divided by h, which is what? What's 4h divided by h? 4. And what is the limit of a constant function as h approaches anything? What is it? If you have an equation y equals 4, what's the limit as h approaches 0? 4. So your derivative at whatever x value you want to look for it at is given by the equation 4. So obviously a little bit funky. If we were to then find f prime of 1, which is finding the slope at 1/6, what would we get? 4. In hindsight, when you look at your function, why does that make sense? Because it's the slope of the, right. It is actually pretty silly for us to go through all this work to find the slope of a line, when all along from Algebra 1 we know that the slope of this line in any line is always the same no matter where you are, this particular one being 4 everywhere on the line. But I just do this just to show you it still works out. Your derivative formula, no matter where you are on the line, no matter what the x value, will always be 4. That's because the slope of a line is constantly 4. Okay? And then to write the slope of a tangent line, this I don't think you would ever do, because I don't believe lines have tangent lines. Right? That's impossible. How could a line have another line that only intersects it at the same slope once? You know what I mean? You can't do it. So lines don't have tangent lines. Well, that's a great question. Do lines have tangent lines? We're going to Google that in a minute. I'm going to say no. That's like kind of a weird concept, but I wouldn't put it past math to have some sort of funky answer to that. Yeah, but it would intersect it more than once, right? It would intersect it infinitely. So the equation of the tangent line would be the line itself, which means is it really a tangent line because it's intersecting it more than once? I'm going to say no. But we're going to double check, because they ask for the slope of the tangent line to that function, so they're kind of phrasing it as if it does have a tangent line, find the answer. We'll get back to that. All right, last one. Find the slope of the tangent line to f of x equals 2 over x at 1, 2. Now, just to give you a visual, this is a rational parent graph. Remember, rational parent graphs are 1 over x. This one has just been stretched vertically by 2, so it's a little bit steeper than your parent graph, which is kind of a hard thing to illustrate, but nonetheless. We're going to look for the slope of the tangent line at 1, 2, which would be right around here. And your tangent line would look like that. So we expect the answer to be negative or positive. We do expect the slope of that tangent line to be a negative slope, certainly. So let's find it. The derivative is the limit as h approaches 0 of f of x plus h, which will look like that, minus f of x all over h. I want to try something new on this because we have time. I can't remember if I'm like getting ahead of myself and telling you more than I really wanted to this early on in the game. But what if we forget the f prime of x, forget getting the equation for the derivative, what if we jumped right into f prime of 1? Don't write this down for a second in case I have to erase it all. But rather than getting the equation for the derivative in terms of x, what if we just immediately looked for the derivative at 1? So we'd have the limit still as h approaches 0. This would be 2 over 1 plus h minus 2 over 1 all over h. Follow? This way we're going to get right to the answer specifically at 1 versus a general equation. You follow? Okay, so this would be I would want to clear my complex fraction. Well, let's see. Can I evaluate right away? If I plug in 0, I'm going to get 2 minus 2, which is 0 over 0. No. So I would want to clear my complex fraction, and my least common denominator of the many denominators within the problem is 1 plus h. So my many denominators are 1 plus h and 1. The least common denominator of those two would be 1 plus h. So when I distribute that here, I'm going to get 2. When I distribute that here, I'm going to get minus 2 times 1 plus h, which I'll get to in a minute, over h times 1 plus h on the bottom. I'm not going to multiply out the bottom because that's not where I was trying to clear fractions. So up top, I'm going to keep this limit as h approaches 0, and it's going to be 2 minus 2h over h, 1 plus h. I love that because 2 minus 2 is gone. I have a numerator that's a monomial with an h and a monomial factor of h in the bottom, so that h will cancel. And I'll get negative 2 over 1 plus h. And now I'm going to reevaluate, and I get negative 2 over 1 plus 0, which is negative 2 over 1, which is negative 2. So I just immediately found, rather than finding the equation for the derivative that can be used at a gazillion points, I just went and I immediately found the derivative at 1 by making all of my x's 1s. So it's an option if you're really only being asked for the derivative at a single location. But a lot of times you'll be asked for the derivative equation down the road, or you'll be asked for the derivative at multiple locations. So it's rather than doing this process for each of those multiple locations, you do that process once for f prime of x, and then you can use that same equation multiple times. So just by tracking what ended up happening here, I think I can see what the derivative equation would have been anyway. Because my 2's are going to cancel. I would have had negative 2, and rather than it being 1 plus h, it would have been negative 2 over x plus h, right? That makes sense to everybody? It would have been the limit as h approaches 0 of negative 2 over x plus h. And then when I pretend that I let h actually approach 0 now, my derivative formula is negative 2 over x. Good? So, couple things. If f prime of x is negative 2 over x here, let's talk again about, well, we know f prime of 1 is going to be negative 2. We expected negative, didn't we? Okay. What's going to happen if we plug in an x value further down, do you think? Do you think the slope is negative or positive? What do you think, Andrew? Slope negative or positive here? Still negative. How negative compared to this previous one? Not as steep, right? So if I do f prime of 5, for example, and get further down the graph, that's going to be a slope of negative 2/5, which is in fact a much less steep slope. Follow? If I go over here to like a negative x value, what would you say about the slope of my tangent line here? Mitch? Still negative. How negative? Very or not so very? Not very, so probably a fraction, right? So let's say I plug in f prime of negative 2. So if that was negative 2, my slope over there would be negative 2 over negative 2. Uh-oh. Did I screw up my derivative equation by trying to take that shortcut? Wait, what are you saying, Abby? Oh, you would have multiplied by x plus h. Ugh. So I lied about this, huh? And that's how I discovered that. So can I just do this quickly? Limit as h approaches 0. Don't mind my work. I'm not gonna keep it really clean. I'm just gonna get the derivative better. So yes, I have to multiply by xx plus h, which when I distribute here is gonna make that 2x. When I distribute here is gonna make that minus 2 times x plus h, all over h x plus h. Yeah, because it was 1, I didn't have to worry about that. So it does affect it quite a bit. So that'll be 2x minus 2x minus 2h. Am I still on the screen? Yeah. My 2x minus 2x still cancels. My h still cancels, but it's negative 2 over x plus h. And when you let, by being messy, I mean I'm not writing down the limit as h approaches 0 18,000 times like you have to. If I wasn't rushing, I would. It ends up being negative 2 over x squared. Sorry. Good catch. Which negative 2 over x squared didn't affect this one. Negative 2 over x squared, that's a lot smaller than we thought. That will be 25. Okay, so now when we go negative 2 over this number squared, it'll be negative 2/4, which is negative 1/2, which does give us what Mitch expected, a negative slope, but not so very negative. And like at negative 1/2, what would you say about the slope here? Positive or negative? How negative? Very, right? That's pretty steep. So if you check that, negative 2 over negative 1/2 squared, that's negative 2 over 1/4, right? Which is negative 8. That's pretty negative, right? Whole numbers are pretty negative, okay? And where is this derivative going to be undefined? When x is 0, right? Which should make complete sense when you know what the parent graph looks like. Of course there's no slope of the function when x is 0. The graph doesn't exist there. A graph can't have a slope if it doesn't exist there. Just like a graph can't have a limit if it doesn't exist there. A graph can't have a function value when it doesn't exist there. So, this is just the introduction of derivatives, and like I said, there's like a whole big long chapter that gets more into depth, allows us to find the derivatives of all sorts of crazy functions that we would never use this technique for. But this technique really capitalizes on that concept of your two secant points. I'm going to say this again. Your two secant points, if this is x plus h, being h units apart. And it's really the slope of your secant line allowing h to pinch closer and closer to 0, which brings your secant line closer to your tangent line. That's the conceptual foundation that you need, and that's where all of this difference quotient stuff comes from. Okie doke. I never asked if you had any homework questions. Were there any questions on your homework?